Go. So again, welcome to today's SCOPE webinar titled Monitoring for Microplastics in the Yukon River, a Blessing and a Curse. Today is the last session in this series featuring Yukon government researchers and collaborators, though we may have a makeup session for one of the talks that was canceled. So we are hosting this talk with respect and gratitude on the traditional territory of the Kwanlin First Nation and Tonquachon Council. My name is Monique Chatterton, and I'm the Science Policy Advisor working with the Office of the Science Advisor for the Yukon Government. I work with Sabrina Cancilla, the Acting Science Advisor, who is here today too. So I am very pleased to introduce our speakers for today. Emily Janin is the Senior Scientist on Water Quality for the Government of Yukon Department of Environment Water Resources Branch. Emily spent over 15 years focusing on water quality and mitigation of impacts from development. Working for the Department of Environment, she takes great pride in providing effective advice and recommendations on water management and water resource protection as it relates to mining and municipal projects. Devin O'Connor is a water quality technologist also with the Government of Yukon Department of Environment and Water Resources Branch. And Devin's time in the Yukon thus far has afforded him incredible opportunities in surface water quality monitoring, fisheries management, wildlife monitoring, hydrometric monitoring, the mining industry, and more. Devin has gained this experience from both the private and public sector and has had incredible opportunities to work with many of the Yukon First Nations to build capacity and improve access to participation in environmental stewardship activities. So with this introduction, I will happily turn the floor over to Emily and Devin to give their presentation. Thank you so much.
Great, thank you. I will share my screen. Is that successful?
Looks great. Yep.
Awesome. So minor adjustment to our title, Microplastics in the Yukon River, Lots to Learn. We made this adjustment because we think it more accurately represents the sentiment of the project so far. And yeah, you'll see that sort of theme of learning pop up a bunch of times throughout the presentation. So starting at the start, how did Water Resource Branch become involved in microplastic monitoring? This stems from a young Yukon lad named Bruce Porter, who at the age of 14 won the junior gold medal in the Canada-wide Science Fair for his work on microplastics in the Yukon River. Bruce used Water Resource Branch's lab for a bunch of his analysis. And during that time, chatting with him and working with him, he made some really compelling arguments as to why Water Resource Branch should get involved and begin monitoring microplastics in a more official capacity. Working with Bruce was definitely a major catalyst for us to undergo microplastic monitoring. And the first thing we had to do was secure, sorry, I'm getting ahead of myself. So based on Bruce's work, we were pretty definitively able to say that there are microplastics in the Yukon River. And this is sort of coupled with growing public and scientific concerns about microplastics in general. You may have seen in the past 10, 15 years, this sort of topic coming up more and more. And that's really compounded by the fact that there's very little knowledge and standardization of microplastic sampling and analysis in the scientific community. Lots of information about oceans, much less about fresh water, and even less about rivers and moving water. So this is an illustration. We had a local artist named Esther Bourdet draw up for us. And we often have Esther create these illustrations for us so that we can share information in a more publicly accessible way. These are types of illustrations that we do commonly share with the public, and it just helps indicate sources of microplastic, how that sort of system functions and relates to our fresh water in the Yukon. So here you can see different sources of microplastic and how it might find its way into the Yukon River. Very simplified. And in order to begin this work, we had to secure funding. And we did so via the YIF, or YESIP Implementation Fund. And this is money that YG administers internally to facilitate the implementation of responsibilities under YESIP. And we successfully made the argument that microplastic monitoring does meet these requirements. So we were able to secure funding for the project. And so the first year was a pilot sampling program. And because there's very little information about this in regards to fresh water, we had to sort of figure out what methods and for sampling and analysis we wanted to use and that were going to work for us. So trying to figure out these appropriate analytical and sampling methods, we picked a location shown on this map here, the Yukon River upstream of Takini River. And this is a site that we visit monthly already. So we felt that if we did continue long-term monitoring of microplastics, it would dovetail nicely being downstream of Whitehorse, which you might expect would be a source of microplastic. And we figured it was a good candidate for our pilot program. The sampling event consisted of Bruce, a Council of Yukon First Nations representative, the Core Geo staff that we contracted out to help us with this project, and Water Resource Branch ourselves. And our first sampling method we tested, our pilot sampling event occurred in the winter. We knew that winter sampling was going to be the hardest, just the difficulties that come with handling liquid water at negative temperatures. So we figured if we could make the winter sampling happen, summer would be easy enough. So this first method pictured here, we would expect that the Yukon River would have quite low levels of microplastics. So this meant that we wanted to sort of take a large volume of water and reduce it to a smaller volume. So in the case of the sieving, we used a 45 micron sieve and 20-liter pails, and we poured 100 liters of water through the sieve. And after that, on the left photo there, you can see flushing the sieve with DI water, getting all of that material trapped in the sieve down into the bottom corner, and then flushing that into a 1-liter bottle. This meant that, shipping 100 liters of water is impossible, but reducing that to 1 liter made it much more effective, and we could still be analyzing a large volume of water. You can also see in the photo, we're wearing these orange jumpsuits, and they're cotton. And the idea here was that, most of us, our winter gear is synthetic and contains plastic itself. So the cotton jumpsuit was intended to prevent us contaminating the samples via our own clothing. And you can imagine the difficulties of trying to get liquid water through a sieve at negative temperatures. It was quite difficult. You can see tinfoil covering the open containers to prevent any contamination there. So this was one method we tested. And on the same day, the next method we tested was using a pump and a filter. And you can see in the right-hand photo, we have a pump going into an auger hole and pumping water out of the river and through that little white filter on the left. So again, we put 100 liters of water through this filter, and we monitored that by filling a 20-liter pail and tipping it 5 times. And same 45 micron filter. And again, some difficulties with liquid water in a pump, and filter being difficult to open afterwards to get and analyze. Some concerns about contributing more microplastic as we opened the filter. So some difficulties with this method as well. You can see it's quite equipment intensive. We needed a pump, a generator. So not the easiest to mobilize and conduct this form of sampling. And the next we did was just a straight up 1 liter grab sample from the river. Now, our concern with this method was that the volume was so low that if we had 2 samples at the same location, one sample might have 1 microplastic particle, the next might have 20. And while they are both quite low, compared to each other, they're very different. So the relative difference between each sample could be very great, taking such a small sample. Additionally, we use these vials pictured here to spike samples. And this is microplastic we sourced, I believe, from the University of Alberta. And we used these microplastic particles to add a known quantity of different sizes and colors to a sample. And this would allow us to test if the different laboratory methods could accurately and precisely quantify the microplastics in the samples. So spiking these samples was another way that we could test analytical methods. And so the analytical methods that we tried, the first was just a basic microscopy. So in our lab, we have a microscope, and Bruce painstakingly looked over all of our, a group of the microplastic samples. And the two photos at the top there are different microplastics that were identified via this analysis. On the left, you can see some sort of maybe mesh piece of material, and on the right is a fiber. And there's a really ingenious way of checking if they are in fact plastic. You can imagine looking at a filter through a microscope, it would be hard to identify if something's organic material or sand or any other form of material or sediment. And what we would do is have a candle with a pin, and you could heat your pin and, looking through the microscope, touch the particle. And if it melted, you knew it was plastic. So it was quite basic and rudimentary, but pretty effective. And similarly, we had ALS do just a fancier form of this microscopy, where they use a fluorescent tagging dye that absorbs into plastic materials. And then they take a bunch of static images, and it makes it quite a bit easier to count these materials, and no need for a hot pin test. So these 6 images on the lower right, you can see are some of those images from their fluorescent tagging. The next analytical method we tested was a particle size analysis at a UBC lab. And basically there was a shortcoming with this method was that it could tell us a number of particles and the size of particles, but not necessarily the composition of particles. And that's obviously quite a crucial component of the analysis for us. So this wasn't a very effective method for us. And the last one we tested was a spectroscopy. And these are different ways that you can beam radiation and light at molecules. And the way that the light is diffracted tells you a bit about its composition. And one of the major downsides of this was that it does not tell you the material itself. It tells you an elemental composition, and it kind of leaves it up to it would leave it up to us to determine what those elemental compositions formed. So you know, oxygen, carbon, nitrogen could be in the water, but not necessarily in the form of plastic. So there were some difficulties sussing out what was plastic just based on elemental composition. And so after doing all those sampling methods and having all those analytical methods run, we took the results of our pilot program and we tried to determine what methods were going to work for us in the Yukon. And in doing all of this, we answered a couple questions, but we created many, many more questions. So a brief sidebar here. We talk about blanks in the rest of the presentation. And for those of you who don't deal with water sampling or don't know about QA/QCs, we have different forms of blank samples that we collect or perform with water quality sampling. And they're a form of quality assurance and quality control. And what they allow us to do is increase certainty of our sampling methods and ensure that we're doing things properly. So the first form of blank that we would use is what you'd call a field blank. And this is where the lab provides us with a jug of deionized water that we know is clean and provided by the lab. And in the field, we complete a sample using that water. And when we submit it to the lab for analysis, it should come back as empty or uncontaminated. And if there is contamination in the field blank, you might be able to determine that the sampler contributed this contamination in the process of completing the sample. So field blanks allow us to determine, is the sampler inadvertently adding contamination or not? The next we would do is a replicate, where we complete a sample, and then we of real river water. And then we immediately do a second sample of real river water. And this will inform us whether or not the sampler themselves is using a proper technique. Or in other words, can they do the same thing twice? If we submit two replicates or two identical samples to a lab, in theory, those results should come back identically. And if they don't, that's a flag for us that perhaps the sampler, again, did something wrong. And the last one would be a travel blank. And a travel blank is filled in the lab and sealed with DI water, and it is never opened. We bring it into the field with us. It travels with us for the duration of the trip, and we never open it, and then we submit it to the lab for analysis. And again, in theory, that sample should come back as clean and uncontaminated. And if there is contaminant detected in that travel blank, it could tell us that there is something in the environment or travel process that is contributing, the lab environment. So once they get that travel blank to the lab, if it has any contaminants in it, it was likely contributed during shipping or their handling in the lab environment. So I mention these things because one of the confusing aspects of the pilot program results were the results from our QA/QC samples. And what we found was that the Yukon River samples ranged anywhere from 7 to 37 particles, microplastic particles per liter. Now, our unopened travel blank had microplastic in it. And then our opened travel blank had more microplastic particles in it. And our sieve control and positive spiked controls, they had interesting results as well. The spiked sample had triple the microplastic we had actually put in. So this raised a bunch of questions. Is the microplastic breaking down? Is atmospheric deposition significant? Once we open that travel blank, is the atmosphere really contributing that much? So again, we couldn't definitively say anything with these results. We had to know more. So what this indicated was that there are sources of contamination everywhere, including the air, and how to narrow down precisely where that's coming from was going to be difficult. So the recommendations from our pilot study suggested that the 1 liter grab samples seemed to be the most effective, just based on how much less contamination there was potential for. So handling sieves and buckets of water in the open air, based on our blank results, might experience a lot of contamination. Whereas opening a 1 liter bottle, submerging it, filling it, and closing it spent much less time exposed to the atmosphere. So there was much less opportunity for contamination. And it's simply easier. You don't require generators, sieves, buckets. With the sieving method, we had a burner going to keep DI water warm, so we could keep those sieves thawed. And it was very cumbersome and just not easy to hand off to someone else if someone else had the desire to sample microplastics themselves. That wasn't going to be an easy method for anyone and everyone to pick up and run with. And then, because the 1 liter volume is so low, we wanted to offset that by essentially doing 5 replicates per sample. So when we say we collected a sample, with microplastics, it's actually 5, and in theory, they should be identical. And this would help compensate for that small volume, give us more certainty in those results. And the analysis we chose was the fluorescent tagging with ALS. This was the only method that told us the quantity of microplastic particles, the different sizes, and required no real interpretation to know what microplastic was in the water. Each other method kind of required some post-analysis interpretation. So these were the recommendations based on what CoreGeo worked up from the pilot study results. And that's what we carried forward with. And so our second year of this project, we monitored on the Yukon River again, and this time we chose 5 stations. And these 5 stations from upstream to downstream were Tagish, just at the Marsh Lake Dam, downstream of Marsh Lake, at our regular site, Yukon upstream of Takini. We sampled in Carmax and we sampled in Dawson. And these samples were all collected in the same week. And what this would allow us to do is perhaps make some conclusions or get a better understanding of how it might change from upstream to downstream. And we also did 2 sampling events, one of which occurred during open water and one of which occurred through ice again. And this would give us further information about potential seasonal changes based on hypotheses that atmospheric deposition was quite significant. Sampling under ice might shed some light on that hypothesis and confirm or disconfirm that. So the 2 events, yes, one open water, one through ice. And what we found there was, based on the fact that there was microplastic present in all our blanks, we wanted to do more of a thorough investigation of blanks so that the information was more valuable. We could start to do some statistical analysis. And so one of the things we did was submit, I believe, 30 blanks, and we tested different containers. We tested different, we tested different containers, different styles of QA/QC, so travel blanks, replicates, field blanks. And we also had the lab hang on to a sample for 30 days to see if there was any change over time. This would all provide more insightful data for us to compare with our actual results. Yeah, sure.
So we'll go into the results a little bit. And before we do, I wanted to share this illustration, which basically showcase what we did. So we took the sample along the 5 stations, as Devin mentioned, and then the purpose of this study is to actually get the data and share the data. And that's one of the reasons we are here today, is to share the data that we have observed and measured. And I think, microplastic is kind of a new science. So, we are just starting to look into it. And so the more we share, the more we can collectively learn. So if people have any, willingness to share with us, we are very, very happy to receive information. And now I'll talk about the results a little bit. And I want to give credit to CoreGeo because those are the samples that we did last year. So Water Resources did the sampling, as Devin mentioned, and then CoreGeo did all of the data analysis and reporting. And you can actually find this data on yukon.ca. It's available to everyone. And I'll start with, so this table presents the data from September last year. And I will start by highlighting the blanks. So first of all, there's 34 samples of the blank, and Devin mentioned that, we did a lot of blanks, and I have another slide about that after. And here I want to highlight that the mean was 30 microplastic particle per liter. So that's just the blank. So as Devin mentioned, we did 3 blanks, which is a bottle that travels and comes back to the lab, and we did field blanks. So for 3 blanks, we did blanks, so deionized water that is in HDPE plastic bottles, so it's high density polyethylene plastic. We did some that were in glass jars. We did some blanks that would travel from the ALS lab where we get the deionized water, and it does go to the Cincinnati lab in the US where they analyze microplastic. And we did the same, except that the lab in Cincinnati hold on to the samples for 30 days. The samples were in that plastic bottle, and we wanted to see if the degradation of the bottle would cause any more plastic in the analysis. We also did field blanks, so those are the ones that the bottle that we take that we take results. We actually pour in the DI in the field, and we did that in glass bottle and plastic bottle to see if there was any difference. The result was that there was actually not much significant difference, and we did the statistical analysis. We didn't see any conclusion jumping at us. What we've learned is that whether we use glass or HDPE plastic doesn't make a difference. If we age the bottle in the lab, it actually doesn't increase the microplastic in the water. And the DI water from the lab itself, which is, clean DI water, but it's produced in plastic, it's a machine that produces the DI water. It actually has some plastic parts, and that water does have microplastics. So no matter what we do, there is microplastic in the water. I think that's the conclusion of it. So back to this table, I want to point out the results that we got at Tagish. So the mean count is 72 microplastic particle per liter. So it's higher than the blank. So definitely there's more particle there in Tagish than anywhere else in the river. And that table below is the January samples. So again, Tagish is higher. It's actually much higher than the blank. 563 is the mean out of the 5 samples. I also want to point out the Takini River samples, which are actually in the Yukon River, just upstream of the Takini, and it has 300. So those two came out as much higher than the blank. So we know that there's definitely something there. Just a quick overview of the findings. The Tagish station had high microplastic in both sampling events, in the open water season and in the ice covered season. The Yukon River downstream of Whitehorse by the Takini had high microplastic, but it was in the winter only, which is interesting. We would have expected maybe the other way around. And a little bit of a quick note on particle size. So through the lab analysis, we can actually distinguish whether there was much smaller particle or much bigger particle. And you can imagine the plastic bag, which is a microplastic, degrades into smaller and smaller and smaller pieces. So the larger the particle, the closer to the source they are. And as the plastic degrades, it becomes much smaller. And we actually had smaller particles in Dawson. So it means it kind of reinforced the fact that perhaps the plastic does degrade as it goes down the river. And also beg the question whether there is a local source in Tagish, because in both sampling events we had higher count and larger particle in Tagish. So we are doing more sampling, and we'll see what the next results are telling us.
So this brings us to this year of the program, and we've already collected our open water sample for this year. So our through ice sample will be collected sometime between January and March. And we'd like to continue the seasonal monitoring using the 5 times 1 liter replicate method. And this will just help us create a longer data set. So the more data you have collected, the more valuable it becomes. And we'd really like to continue with that. If the opportunity arose that we could potentially sample upstream and downstream of a known source of microplastics, so a water treatment plant or storm or a snowmelt runoff point, that would give us some more insight about sources. And finally, the big takeaway from all of this has been we really need to work to develop industry standard methods. And we are in the process of this via a national working group on plastics in stormwater. And really what we find to be consistent across the board is that there is no standardized, here is how you sample microplastics. It very much varies from group to group and from water body to water body. The ocean and lakes and rivers, the information we saw all varied quite significantly. So having a standardized method would allow us to hand off this sampling to anyone else and make our results comparable against each other without having to do any sort of interpretation or anything like that. So some of the ideas we'll leave with you to ponder. Based on some of the issues we were encountering with our blanks, we were unable to locate microplastic-free water. And one thing we didn't mention in the blanks section was, because of this issue of all our blanks being contaminated, even the ones that came straight from the lab, we decided to just collect a sample at a groundwater well that we monitor, that we know to be very deep, very clean, and has a rapid recharge. And so we collected groundwater to see if that could be used as perhaps a facsimile blank, where if there is no microplastic in that groundwater, at least we have identified plastic-free water. Unfortunately, that groundwater sample had microplastic in it. So if we can't locate plastic-free water, how do we know what is detected and what is baseline? How do we define the detection limit? It becomes very difficult to do the sort of standard conclusions that we would do based on normal QA/QC results. So based on that, how do we know we have robust conclusions? It's a very difficult thing to say definitively that our results are accurate and precise. And how should we report this data when the QA/QC results are skewed? So how do we share this with members of the public and other scientific groups? And this brings us back to the need for standard methods. And finally, is there value in reporting the total mass of microplastic per volume as opposed to the number of particles? Because the size can vary so greatly, perhaps it's not as insightful as measuring just mass entirely. Do you have anything else you wanted to add to that?
No, I'm just looking forward to any comments or questions from the audience. I would love to chat more about that. And
yeah, at the bottom here, you can see microplastics are one pager on yukon.ca. I tried yesterday, I just Googled YG microplastics, and it was the first thing that came up. So that information is quite easy to find on yukon.ca, but our emails are there. If you'd like to send us any questions or comments, we'd be happy to have them.
And then there's the one pager, but there's also the 2 reports that Geoscience have done. So those are like more detailed reports. So all of the data that we have is in there, and it's available online.
And that's about it for what we have to say. You can open up to questions.
Thank you so much, Devin and Emily. That was a really interesting journey that you went on with all that sampling. And yeah, let's see if anyone has any questions. Bob. Okay, Bob.
Good afternoon. One of the things I do in my retirement is a bit of work with the Arctic Council, and specifically the Arctic Monitoring and Assessment Program. And they've been working with another one of the Arctic Council working groups, PAIM, Protection of Arctic Marine Environments, looking at litter and microplastics. And they have done a bunch of work on trying to come up with monitoring protocols. I'm wondering if you're tied in with that at all. There's an expert working group with them, or if the Canadian national work is tied in at all with AMAP.
Thanks, Bob, and hi. Thanks for the question. Yeah, I am aware of the work from AMAP and the work in the Arctic that relates to plastic, and I understand, so we are not working directly with them, if that's the short answer. The longer answer is that I understand that they monitor plastic, but not necessarily as much microplastics. But I believe that some of the experts of this AMAP group are actually in the CCME working group on CWP. I don't remember what the acronym is, but it's on plastic in wastewater and stormwater.
Right. PSWI.
No. So yeah, as far as I know, but correct me if I'm wrong, and I seen somebody else put a chat, Paul McCartney, put a chat about that. I don't think that they actually speak for what analytical method to use for microplastics per se, to count microplastics in water. I know that they do count plastic and weight plastic in birds and things like that, but correct me if I'm wrong, Bob or Paul, or if you have any suggestions for us.
They are, I'm not sure if they've completely published all the work yet, but they're definitely looking at trying to come up with standardized protocols for microplastic. I can put you in touch with the expert group or the secretariat person at AMAP who's working on that project.
I would love that, but yeah, if you could, that would be great.
Sure.
Okay, thanks, Bob, for that question. Paul, I see you had a similar question. Did you have anything you wanted to add to Bob's question?
No, that's perfect. That's exactly what I was going to say, and I was also going to respond with the saying that I know it is still a work in progress, but the intention is certainly to include microplastics in those guidelines. But yeah, no, that's great, and I appreciate the response and that it is a challenge to come up with those standardized procedures.
Okay, thanks, Paul. I see we have another question in the chat. It's coming from the Core Geo office. They say, thank you for the presentation. And they're asking you, what is the guideline for microplastics in freshwater, if any? How fast do microplastics degrade?
Was that related to the AMAP guideline that Bob and Paul mentioned, maybe? Because if it is, I guess Bob and Paul would be better suited to answer that.
Core Geo office, did you want to speak to that? Is that the basis of your question? Something similar? Okay, I'm not sure, but would you be able to speak to how fast microplastics degrade, or maybe that second part of their question?
No, I don't know how fast they degrade. I guess that's my answer. This is not something that we've looked into. It doesn't mean that the knowledge isn't out there, but it's not something that I'm aware of. I don't know, Devin, if you know more about that.
No, I don't think we came across anything ourselves. I would expect it varies from plastic to plastic, right? HDPE would probably behave differently than other plastics. So I don't think there's sort of a silver bullet answer for that.
Depends. Okay.
As far as the guideline goes, perhaps we could speak for the work. So CCME has a strategy, and one of the strategy relates to plastics. And as part of that, there's a couple of working groups. There's the one that David is part of on wastewater, stormwater, and industrial water. And then I believe that next year they will establish one that will be meant to develop standard operating procedures. And I don't know if it's for analytical or for sampling too. But CCME is well aware of the need for some standardization. And CCME, for those who are not aware, refers to Canadian Council of Ministers of the Environment. So it's kind of a pan-Canadian guiding organization, I guess. Oh, and I see the AMAP guideline in the chat. Thank you, Bob.
Yeah, thanks for putting that in there, Bob. If anyone wants to see that link, just open the chat and you can find that link there. Okay, I see we have another question from Sabrina.
Hi there. Sorry again for my confusion over the audio earlier, user error. Anyway, I have two questions, but I'll only ask both if another hand's not raised in the next minute. The first is about the visuals that you showed, the posters. You might have said, or it might have shown it on the slide itself, but I couldn't see who the artist was. And I love that different way of showing information. So I just wondered if you could share.
Yeah, the artist is Esther Borde. Perhaps we could write her name. The name of our company is Yukon Graphic Illustration, I believe. And she's a wonderful woman. She is a geologist from training. She has a PhD. She worked for YGS at some point, and then she decided she wanted to switch over into illustration, but she does illustration of scientific concepts, and she's been really great to work with. So I would highly recommend her to anyone who want to do illustrations. I believe that she worked with the Dawson and Youth Plan, some salmon work with First Nation people, and a bunch of different science.
Okay, great. Thank you so much for sharing that. I don't see anyone else's hand up, so I'll keep going with my second question. First, just commending you on the involvement of on working with youth, and it's really neat to see that this project was triggered by that Bruce Porter's science fair project. And I just wondered about, you mentioned he was able to analyze his samples at the Water Resources Branch Lab. Is this something that you guys have done before or will do again, working with, like, allowing youth access to your lab? Or I just am curious about that experience and in general, and the lab experience in particular.
Yeah, definitely. We did some work with Y2C2 this summer, and that also included some work in our lab where we worked through some fecal coliform analysis with them in our lab, got them some hands-on experience there. And we also commonly share things like instruments and other equipment with Wood Street, for example. So anytime we can, we really like to facilitate that, and it's a lot of fun. Although Bruce did make our lab smell like whitefish for like 2 months because it involved whitefish stomachs. So I give him a hard time about that. But yeah, it's great fun working with these kids.
Awesome, thanks so much.
You do the Water Week presentation too, and one is on microplastic, but also on other water topics. So that's where Devin and other people go into the schools and talk about water and different water science. So they are not coming into our lab, but that's a connection that we try to, do. We actually do it every year. Awesome.
Amazing, thanks so much.
And so perhaps I could speak a little bit more. I see Sridin is on the call and she might be able to speak for that a bit more, but I believe that Bruce, after he's looked at microplastic in the water, then he looked at microplastic in fish stomach. And I believe that was with Mary Gamber. And yeah, so that's why the lab was thinking for some time, and he's still involved. Devin was presenting yesterday at a plastic conference and Bruce was there. So he's still like very involved.
Thank you. I have a question. So maybe I missed it, but I was wondering about the source of the water for the blanks. I know you talked about finding that deep groundwater source that you thought might be clean, and you still found microplastics in that source. But other than that, like, what was your typical source for the blanks for the?
So generally that water comes from like an ultra pure deionized water machine. So we would just call it DI water. So that's generally the water that the lab provides for us to complete things like field blanks, and that's what they fill our travel blanks with. And I believe the comment from ALS themselves was something to the effect of microplastics are ubiquitous and we simply cannot get a filter that removes them all from our water. So they weren't willing to say with confidence that they could provide us with water without microplastic in it. So of course, any other contaminant, like you wouldn't get, chromium in a DI water sample, for example, but microplastic is very different from any of these contaminants that we generally deal with.
Do you know if there's research being done to find ways of filtering it out, even to create a good blank
My
source?
guess would be yes, but I don't know of any specifically.
I don't know either. I think so. With Scorgio, we did a little bit of statistics work, and for regular contaminant like chromium, for example, there is a method where we define what the detection limit is, and if it's under the detection limit, we report it as non-detected, which means okay, there shouldn't be any of that chromium, for example, or things. I think for microplastic, we could perhaps use the same approach, but the definition of the detection limits might be different, because it's a different type of analysis. Basically, we count something as opposed to detecting a signal for something. So I think I would like to explore more, how can we define a detection limit, basically? And could we agree on an appropriate, adequate definition for it? And then anything above that, then we say, oh, it's detected, and this is the number that we have. And anything under, I was like, well, we know that there are some, but we cannot quantify them. Or so I think that's where I would like to see this going.
Thank you. Okay, I see we have one more comment. Sruti, yes, I see you have a question. Thank you.
Yeah, well, it's kind of an extension to Emily's point there, because I think in terms of detection limits, it's varying depending on the methodology that you use. And with ALS itself, they do the fluorescent tagging, and then they've got a sort of microfluorescent FTIR methodology going right now, which allows you to detect even smaller particles. So as we keep going, like with technology, as we keep going, the smaller the detection limit, we're going to keep seeing plastics no matter what. So I think it really depends on the methodology that you develop and the size range that you want to see, and the particular kind of plastics that you might want to target. So it's going to really, it's a very open-ended sort of a field there, because you're going to really need to bring down your methodology as to what you want to look at, and the type of analysis that you're going to be using.
Thanks, Ruthie.
And thank you guys. Great presentation, by the way.
Thanks.
Any other questions? I have another one. What are your plans for the future of this research in the Yukon River? Do you I think you said a little bit about it at the end. I'm just curious, like, are you going to keep going? What are you going to do next?
Well, the immediate next would be this fiscal year, we'll do a through ice sample. Sometime between January and March. And then I believe it would be a matter of applying for YIF again for next year's sampling. So I think the longer we do it, the more compelling argument we have to keep doing it. Because like I said, data is more valuable the more of it you have. So I think it only gets stronger the longer we do it.
Now it's also participation in the national working groups too. I think that's very important as well. So that's part of our work.
I see the question from Corgio again. How'd you sample the groundwater? We bought a very expensive stainless steel baler and a spool of stainless steel aircraft cable. And we purged the well. I can't remember the precise volumes. It's very deep and
200 feet.
Yeah, and it's got quite a volume in it. So we purged the daylights out of it, and then collected our 5 replicates of that groundwater well as well.
And a beta, for people who don't know, it's like some sort of a metal tube. That's what we use to collect the water. So that basically using the metal things meant that the water collected from the well would not be in contact with plastic until it gets to the surface.
Great, thank you. Any other questions? Okay, I think that's it. Thank you so much, Emily and Devin. That was really interesting. A great presentation. Really appreciate it. And thank you everyone for coming and attending this webinar series. I hope you enjoyed it, and I will make the recording available. If you want to share it with anyone, you can do so. Okay, thanks everyone.
Thank you, everyone.
Excellent, thank you.
Susie, I would love to connect with you this afternoon if you have a minute.
Yeah, for sure.
Okay, thanks.
Okay, thanks.
Take care.
Bye,
Thanks.
have a great day.